A prime number is a natural number that has exactly two factors. It's divisible by 1 and itself only. A basic method to check if a number is prime is to traverse numbers from 2 to square root of n, and if one of them divides n, then n has more than two factors, therefore it's not a prime number. We're traversing square root of n minus 1 numbers, so the time complexity is O of square root of n. Now, what if we want to find all prime numbers up to n? For example, if n is 20, we want all prime numbers that are smaller than or equal to 20. We get 2, 3, 7, 9, 11, 13, 17, and 19. We can just apply the method we've seen now to each number to see if it's prime. We apply it to 1, 2, 3, and so on until n, while storing all those with which the function returns true. And our function that checks if a number is prime costs O of square root of n time, so the total cost to apply to numbers from 1 to n will be square root of 1 plus square root of 2 plus square root of 3 and so on until square root of n. This sum is the sum of square root of I where I goes from 1 to n, which is an O of n times square root of n. We got an O of n times square root of n time complexity. But we have more clever ways to find primes up to n. The one we will see today is the Sieve of Eratosthenes. The main idea is that if we have a natural number x greater than 1, then all multiples of x greater than it are not prime, because x is a factor of them. So we traverse all of them and set them to not prime. Then we move to the next number and we set all of its multiples to not prime, and so on. Let's see an example to better understand. We want to find all primes up to 50. We first create a boolean array isPrime where isPrime of I says if the number I is prime. At the beginning, all values are true. We assume that each number is prime until we find the third factor. We know that 0 and 1 are not prime. We set isPrime of 0 and isPrime of 1 to false. Now we can start. The first prime number is 2, and 2 is a factor of 4, 6, 8, 10, and so on until 50. We set them all to false. All of these have a factor other than 1 in themselves. It's 2, therefore they're not prime numbers. The next prime number is 3. Same thing, all its multiples are not prime because 3 divides them and is different from 1 in themselves. We traverse multiples of 3 and we set them to false. 6, 9, 12, 15, and so on. By the way, when I say multiples, 3 is a multiple of itself, but we don't include it. We don't set it to false, because it has to be different from 1 in itself to say that it's not prime. Let's continue. The next prime number is 5. Multiples of 5 are 10, 15, 20, and so on. We set them to false. Next prime number is 7. We set its multiples to false. Next one is 11. We set its multiples to false. Then we have 13. Its multiples are 26 and 39. We set them to false. Then 17. Its only multiple is 34. Then 19. Its only multiple is 38. Then 23, its only multiple is 46. Then 29, no multiple smaller than or equal to 50. Then 31, same thing. 37, same thing. 41, same thing. 43, same thing. And 47, same thing. We finished traversing the array, so cells that are still true are cells of prime numbers. We have 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, and 47. Before moving to code, you may be wondering, why did we traverse multiples of prime numbers only? For example, when we were at 3, after it we directly moved to 5, the next prime number. Why did we skip 4? We skipped 4 because it's not a prime number, which means that it has a smaller factor that we traversed before, 2 in our case. And because of that, we already set to false multiples of 4 when we were at 2, because multiples of 4 are also multiples of 2. We've set them to false before. In code, we create a boolean array isPrime of n plus 1 elements. We set isPrime of 0 and isPrime of 1 to false, and we can start. We start traversing from 2, so I goes from 2 to n plus 1. Inside it, we traverse multiples of I only when I is prime. We first put a condition if isPrime of I. If it's prime, we traverse its multiples. J starts at 2 times I, the first multiple of I after itself. It stops at n plus 1, the end of the array, and we add to it I at each iteration to traverse multiples of I only. For example, if I is 7 and n is 50, j will start at 2 times 7, which is 14, then it traverses 14, 21, 28, 35, 42, and 49. And inside the inner loop, we just set is prime of j to false. J is a multiple of our prime number I. After the loop, we return indexes I where is prime of I is true. What about the time complexity? We start with 2 and we traverse its multiples up to n. The cost is n divided by 2 because we have n divided by 2 multiples. Then we move to 3, we traverse its multiples up to n. The cost is n divided by 3. N divided by 3 because we keep jumping by 3. Then we have 5, traversing its multiples costs n divided by 5. Then 7, traversing its multiples costs n divided by 7. Then 11, traversing its multiples costs n divided by 11. And it continues like that. Basically, we're doing the sum of n divided by p where p is a prime number and smaller than or equal to n. Which is n times the sum of 1 divided by p where p is a prime number and smaller than or equal to n. And this sum is called the sum of the reciprocals of primes. It's an O of log n. Multiplied by n, we get an O of n times log n time complexity for the Sieve of Eratosthenes. And for the space complexity, we have O of n because of the is prime array. We still have some optimizations to do in our code, even if we want to reduce the time complexity, but we will make it faster. The first optimization is that in the inner loop, j can start at I times I instead of 2 times I. The reason behind it is that 2 times I is already set to false, because it's a multiple of 2. If we decide to start at 3 times I, same thing, already false, it's a multiple of 3. And it continues like that. The first number that can be true but should be false is I times I. Second optimization, instead of jumping by I, we jump by 2 times I if I is different from 2. To avoid multiples of 2, we already set them to false before when I was equal to 2. For example, if I is 3, if we jump by I, we have 6, 9, 12, 15, 18, 21, and so on. Half of them are multiples of 2. It's useless to traverse them again. When we jump by 2 times I, we get 9, 15, 21, and so on. No multiples of 2. Last thing, because j is starting at I times I and stops when it reaches n plus 1, then we can avoid all values of I where I times I is greater than n. This is why I can stop at square root of n instead of continuing until n. All numbers after square root of n will have no multiple to set to false, useless to traverse them. And now we have a pretty good Sieve of Eratosthenes function. With n equal to 100 millions, this function took around 15 seconds while the first one took around 35 seconds. We reached the end of this video. We learned about the Sieve of Eratosthenes, one of the fastest algorithms to find primes up to n. But there are other ones that you can learn about, like the Sieve of Atkin. I hope that you enjoyed this video. If you did, like and subscribe to the channel, and see you in the next one.